Good morning to all. Today's topic is torque measurement in Module 6 of course Metrology and Instrumentation. This topic will be presented in two parts. As per our syllabus, we needed to study various kinds of dynamometers such as mechanical, hydraulic, and electrical. But before that, have a glance at the importance of torque measurement. The measurement of torque is essential in the determination of mechanical power. The power P is related with torque T by the equation P is equal to 2 pi nd by 60, where N is the RPM of the spindle. Moreover, the torque is important for evaluating the performance characteristics of machines. The torque measuring devices are popularly known as dynamometers. There are various kinds of dynamometers. If the machine generates power, the dynamometer employed must have the capacity to absorbing that power. Such dynamometers are called absorption dynamometers. The absorption dynamometers are further classified as Prony brake dynamometer, rope brake dynamometer. Both Prony brake and rope brake are coming under mechanical dynamometers. Then the hydraulic dynamometer and eddy current dynamometer, or otherwise the electrical dynamometer. The transmission dynamometers are used to sense torque at particular location. These are otherwise known as torque sensors. And the third one is the servo controlled dynamometers. Let's start with a block type Prony brake dynamometer. It is one of the simplest, inexpensive and most popular absorption dynamometers invented by Gaspard de Prony, a French engineer, in 1821 to measure engine power. So in construction, it contains two wooden blocks mounted on either side of the flywheel, and this flywheel is fitted to the shaft of the engine. A lever arm is fixed on one of this wooden block, and the other block is connected to an arrangement, a nut and helical spring arrangement, to tighten the blocks. The tightening the block is to enhance frictional resistance between the block and the flywheel. Let's assume that we don't have this weight and the engine is not running. Then the extended portion of this lever, that is the weight of the extended portion of this lever, is balanced with this counterweight. And in balanced position, the lever will maintain a position between these two stops. Stops are provided to prevent the lever to be moved to its extreme positions, both in clockwise and anti-clockwise direction. Now in the second condition, let's assume that the engine start running and the shaft is running in anti-clockwise direction. Because of the friction between the flywheel and the wooden blocks, the shaft tends to move the lever in anti-clockwise direction, but it will be prevented by this stop. So what we will do, we will add weights one by one over here. So at a particular point or a particular weight, adding up to a particular weight, the shaft will again move downwards and it will be again in this equilibrium position. It will maintain the balanced position. So we will note this weight, the quantity of the weight we have added to this lever. Now we will note this weight as W, and the length of this lever from the center of the shaft to the center of the suspension of weight is taken as L. So this W into L is our torque. So this torque is now balancing with the torque of the engine. That is, this will be equal to the torque produced by the engine. This is how we are measuring the torque produced by the engine. Now, if we know this torque and the rotation per minute of this engine shaft, we can calculate the power output of this engine as 2 pi nd by 60. In advantages of Brownian brake dynamometer, it is simple in construction, less cost, and suitable for measurement of small power. And the disadvantages are, due to wear of the wooden blocks, its use is limited to small power measurements. In addition to that, a cooling system is required for its operation, and the measuring arrangement may be subjected to oscillation, especially when the machine torque is not constant. Another mechanical dynamometer is a rope brake dynamometer. It consists of two or more ropes wound around the flywheel fixed to the shaft of the engine. One end of the rope is connected to a spring balance, and the other end is connected to the loading arrangement. Cooling arrangement is provided to carry away the heat produced by friction between the rope and drum. Let's assume that the engine is running at a fixed speed in anti-clockwise direction as shown in this figure, and now we are adding some more weight to this loading device. Maybe a 1 kg or 2 kg load is adding to this loading device. Then what will happen? The speed of the engine will reduce. So in order to make up that reduction in speed, so in order to again making that engine speed to the set speed, we have to increase the speed of the engine. That's by supplying additional fuel we are increasing the speed of the engine. So supplying additional fuel means the engine is now producing additional power to make up this load. So we know that the additional power produced is proportional to the dead weight added here. So in this case, the torque is calculated using this equation: tangential force into radius of the wheel. That is, tangential force is the net force, that is W, the added weight, minus spring balance reading multiplied by effective radius. Effective radius is nothing but it is the half of sum of diameter of the flywheel and diameter of the rope. So brake power is calculated from this torque as 2 pi nd by 60 in watts, or if you want it in kilowatts, it is 2 pi nd by 60,000 kilowatts. The advantages of rope brake dynamometers are: one, it is simple in construction, then used for wide range of power, that is from smaller to bigger power generated machines, then used for long test with little overheating. And in disadvantage side, it is less accurate because of change in coefficient of friction with the temperature. And the second one is, again, this system also requires a cooling system. In the second part of this topic, we shall discuss about hydraulic dynamometers and electrical dynamometers. Thank you for watching and stay safe.